Hi everyone. We're going to practice writing molecular, complete ionic, and net ionic equations in this video. And in our first example, they want us to write these three equations for when we mix potassium carbonate. Notice we have an aqueous solution, meaning it's dissolved in water, with another aqueous solution containing magnesium sulfate. So we usually begin with the molecular equation, and that shows the full chemical formulas of everything in the equation. So I'll begin with our reactants. Potassium carbonate, aqueous, reacts with or gets mixed with magnesium sulfate. And now I have to predict the products. So I like to kind of go on some scrap paper and kind of remind myself, what ions does potassium carbonate consist of? That would be a potassium ion and carbonate ions. And right now, since this is just scrap paper, I'm not so worried that there's two potassiums for every carbonate. And directly underneath, I'll do the same thing for magnesium sulfate. It consists of magnesium with a +2 charge and sulfate with a -2 charge. And now I'm going to crisscross. My products are going to be potassium sulfate. And I have to be careful when I write the formula. Potassium is a +1, sulfate is a -2, so I'm going to need two potassiums. That's the formula for potassium sulfate, and we have to decide if that's soluble or insoluble. Well, we've got this rule here, all sulfates are soluble, and we don't have an exception, so this would be soluble. And then our other product is going to be magnesium carbonate, and magnesium is a +2, carbonate is a -2. The formula of that compound would just be magnesium carbonate, and I've got to decide if that's soluble or insoluble. Well, all carbonates are insoluble, and I don't have an exception. That is our precipitate. If you want to, you could have used S here for solid. The next thing we should do is make sure that this equation is balanced, and I do think that it is balanced. So now on to the complete ionic equation, which shows how these species or solutes actually exist in solution. Our first compound to consider is potassium carbonate. That is a soluble ionic compound. It's going to dissociate 100% into two potassiums and one carbonate. I have two potassiums because of this subscript. The next compound to consider is magnesium sulfate. Again, we have a soluble ionic compound. It's going to dissociate 100% into a magnesium ion and a sulfate ion. Now on to the products. Potassium sulfate, that's another soluble ionic compound. That's a strong electrolyte. It's going to dissociate into two potassium ions. And again, there's two because of this subscript 2. And one sulfate. And then I have the precipitate, and I'm just going to leave that alone. That is not going to dissociate or even dissolve in solution. So that's the complete ionic. The net ionic equation just shows the species that participate in the reaction, or in other words, this is where we cancel out the spectators. Here, the spectators would be potassium and also the sulfate. Nothing happened to those ions. They just were kind of the spectators. So the net ionic equation would be carbonate combines with magnesium to form a magnesium carbonate precipitate. Let's try another one. So here we're mixing ammonium phosphate and calcium chloride. And I'm just going to go on some scrap paper and predict the products. I have ammonium ions and phosphate ions in my first compound, and calcium ions and chloride ions in the second compound. So now I'm just going to crisscross, and the first compound is going to be ammonium chloride. Notice ammonium has a +1, chloride has a -1, so the formula of that compound would just be NH4Cl. And notice that all ammonium salts are soluble. And then the other product is going to be calcium phosphate. So I want to be very careful when I write the formula of this compound, remembering that calcium is a +2, phosphate is a -3. So the formula of that compound would be Ca3, PO4 taken twice. And looking at our solubility rules, all phosphates are insoluble, and we don't have an exception. That's our precipitate. Now to balance, and I'm drawn to the 2 phosphates on the right. I better put 2 on the left, and that's giving me 6 ammoniums on the left, so I'll put 6 on the right. And now I've got to balance the chlorides. If I put a 3 here, I think that does it. So that is the molecular. Now for the complete ionic. So the question we're asking here is, do we dissociate these solutes? So here we go. Ammonium phosphate, yes, we dissociate it. It's a soluble ionic compound. And how many ammoniums do we have? Well, 2 times 3 is 6. So 6 ammonium ions. And then how many phosphates do we have? Well, we would have 2. And now on to the calcium chloride. Well, we're going to have 3 calciums. And then 3 times 2 would be 6 chlorides. And now on to the right. We're going to dissociate this ammonium chloride because it's a soluble ionic compound. We've got 6 ammoniums. And 6 chlorides. And then the precipitate we're going to leave alone. That does not dissociate, nor does it dissolve. That's our precipitate. Now we're going to cancel out our spectators, and I'm seeing ammonium on the left, ammonium on the right, and I'm also seeing chloride on the left, chloride on the right. So the net ionic equation is 2 phosphates combined with 3 calcium ions to form a calcium phosphate precipitate. When you write these equations, you've got to always remember to include charges on everything. Let's do another one. Okay, this one is a little bit different in that it's an acid-base reaction, and I've reminded us of our strong acids and bases here, but I can still use the same strategy. So hydrobromic acid is going to combine with potassium sulfide, and let's predict our products. Hydrobromic acid consists of H plus and bromide. Potassium sulfide consists of K plus and S minus 2. So the first product is going to be hydrogen sulfide. Again, pay attention to your charges. H plus is a +1, sulfide is a -2, so I'm going to need 2 hydrogens. And I hope you remember this is a gas. This is the gas with a rotten egg smell. Our other product is just potassium bromide. Notice the potassium is a +1, bromide is a -1. We can write the formula of that compound simply as KBr. And now you do have to remember your solubility rules. All group 1A salts are soluble. That'll be aqueous. I think we need to balance this. I'm seeing 2 hydrogens on the right. I'll put a 2 on the left. And now I've changed the bromide, so I'll put a 2 here. And I think the equation is balanced now. So that's the molecular. Now in the complete ionic, the question is, do we dissociate these? Well, HBr is a strong acid, so it dissociates 100%. In this case, we'll have 2 H pluses and 2 bromides. And what about your potassium sulfide? This is a soluble ionic compound. It dissociates 100% into 2 potassiums. Again, that 2 comes from the subscript, and 1 sulfide. And we leave our hydrogen sulfide gas alone. And our other product is a soluble ionic compound. We're going to dissociate it 100%. In this case, we're going to get 2 potassiums and 2 bromides. Now for the net ionic, this is where we cancel out our spectators. I'm seeing 2 bromides on the left, 2 on the right, and I'm seeing 2 potassiums on the left and 2 on the right. So the net ionic is 2H plus 1 sulfide yields hydrogen sulfide gas. Let's do another one. Looks like another acid-base reaction. So our first reactant is nitric acid, and it's reacting with barium hydroxide. And now to predict the products, again, I'm going on my scrap paper. Nitric acid is composed of H plus and NO3, and barium hydroxide is composed of Ba2 plus and OH ions. Our first product is just going to be HOH, or water, and we always define water as a liquid. And our other product is going to be barium nitrate. Again, be careful with your charges. Barium is a +2, nitrate is a -1, so we're going to need 2 nitrates in the formula. And if you remember from solubility rules, all nitrates are soluble. And I think we need to balance this. I think I need a 2 here and a 2 in front of the water. Give me a minute to check this. Yes, I think that's balanced. That was the molecular. Now for the complete ionic. Again, you're asking yourself, do I dissociate any of my reactants or products? Well, looking at our first reactant, it is a strong acid, and strong acids dissociate 100%. In this case, we're going to get 2 H plus ions and 2 nitrate ions. And what about our next reactant? That's our base, and it is one of our strong bases. So dissociate it into 1 barium ion and 2 hydroxides. Again, that 2 comes from the subscript. And on the products, water we're going to leave alone. And then our other product is a soluble ionic compound. It dissociates 100% into a barium ion, and we're going to have 2 nitrates. Now we'll cancel out our spectators. I'm seeing barium on the left, barium on the right, and I'm seeing nitrate on the left and nitrate on the right. So the net ionic is 2H plus 2OH yields 2 waters. But I think you know that we could do a little bit better. We always use the lowest set of coefficients. So we would just have 1 H plus 1 hydroxide to form water. That would be the net ionic equation. Let's try one more. Another acid-base reaction. So our reactants are HNO2 and sodium carbonate. And now to predict the products, I'm using my scrap paper. This compound consists of H plus and NO2 minus. Sodium carbonate consists of sodium ions and carbonate anions. So the first product is going to be carbonic acid. Notice that we're going to need 2 H pluses for every 1 carbonate. And there's something special to remember about carbonic acid. But let's write the other product. That would be sodium nitrite. And all group 1A salts are soluble. And maybe we could balance this. I think if I put a 2 here and a 2 here, that ought to do it. But the special thing that I asked you to remember about carbonic acid is that it's unstable and rapidly decomposes into water and CO2 gas. So that's the molecular. Let's write the complete ionic. And again, you're asking yourself, do I dissociate any of these reactants and products? Well, look at this first acid. Is it on our list of strong acids? No, it is a weak acid. And since they only dissociate about 100%, leave this weak acid together. Do not dissociate weak acids. Now our next compound is a soluble ionic compound. Dissociate it. And then water, we're going to leave alone. Carbon dioxide gas, we're going to leave alone. And then this sodium nitrite, we're going to dissociate because it's a soluble ionic compound. We're going to have 2 sodiums and 2 nitrites. Now we'll cancel out our spectators, and I'm seeing sodium on the left, sodium on the right, and I think that's it. So the net ionic equation is 2HNO2 plus carbonate yields water, carbon dioxide, gas, and nitrite ions in the water. So I hope you feel a little bit more comfortable about molecular complete ionic net ionic equations. Keep practicing, and thanks for listening.